All right, so we're going to work through another problem using Newtonian physics. This one says, a student kicks a frictionless puck with an initial speed v0 so that it slides straight up a plane that is inclined at an angle theta above the horizontal. Write down Newton's second law for the puck and solve it for a position as a function of time. And then it asks, how long will it take for the puck to return to its starting point? Okay, so I went ahead and drew, to the best of my ability, a ball going up a ramp at a speed v0 with an angle of the inclined theta. Let's start by thinking of our coordinate system like this, where this is our x and this is our y. It usually makes sense to tilt your coordinate system in such a way that your motion or your acceleration is pointing in the direction of one of our coordinate system. In this case, we're going to point it so our x-axis is pointing in the direction that the ball is moving. Okay, so now that we determined that, let's draw a free body diagram. So what forces do we have? Well, we're going to have a normal force that's going to be perpendicular, so just right there. That'll be our normal force. Then we're going to have a weight force pulling it down. So we'll draw a weight force exerted by the Earth onto the ball, which is equal to just mg. This is the same angle as our theta. There's some geometry you can do, or think of it as just you're dropping your perpendicular, this perpendicular leg here. Theta is going to be between that. Okay, so if we were to do a little right triangle trig, this component right here, that's going to be mg sine theta. And that's equal to the y portion. So you can think of that as being the force due to gravity in the y, or I'm sorry, in the x, for the x component, because that's your horizontal. And then vertically up here, this is just mg cosine theta, and that's equal to the force due to gravity in the y direction. Are there any other forces acting? No, not really, because it's frictionless. So this is kind of like if you had a sheet of ice or something that just has not a lot of friction. So we don't have to worry about friction. It should be everything. We covered all our bases. All right, well, where it wants us to find the equation for the puck's position. The puck's position is going to stay y no matter what. It's not bouncing up and down on the ramp. So if I did the sum of all forces in the y direction equal to mass times acceleration in the y direction, this is easy just to say is 0. Now, there are forces in the y direction. We have the normal force minus, so we have our normal force here, minus this portion. So minus mg cosine theta. Mg cosine theta equals 0. Now, in a lot of cases, when we do have friction, we'll say normal is equal to mg cosine theta. And we do this a lot you probably did this in Physics 1. This isn't going to be helpful in our particular case because there's no friction. Normally, the force due to friction is your normal times your coefficient of friction. So in this case, it would be mg cosine theta times this, our coefficient of friction. But there is no friction. There's no coefficient of friction, so it's all 0. So it's actually not particularly helpful to look in the y direction. But it's worth talking about. Now, if we did, I'm going to think of this, this was more like we would in Physics 1. However, in mechanics, instead of thinking of it, we would say our force is equal to, instead of acceleration, we would say is mass times the second time derivative of position. So what force is in the x direction? Really just the component of gravity, which is mg sine theta. So we would say mg sine of theta is equal to m times acceleration, or the second time derivative of position. You can divide both sides by the mass, and if you do that, you'll see g times sine of theta is equal to the second time derivative of position in the x direction. Now you might say, hey, this is a constant. Gravity is a constant, and sine of theta, the angle isn't changing, so that's a constant. So you could actually quite quickly just use kinematics as one way. So one way is just to use, by recognizing you have constant acceleration. And if you remember from kinematics, we know that x final is equal to x initial plus v naught in the x direction times time plus 1/2 at squared. Well, as long as we let our ball be the starting point of our axis, this is 0. So this simplifies into x final equals our v initial times time, because that's where our velocity is. It's all in that direction. Plus 1/2 our acceleration, which real quick, let's look at the sign that should be there. If we look at the direction that our puck is going, and we look at this, so if we look at this portion of our triangle, notice that's behind that bit where we're kind of saying the origin is. So because this is to the left of that, we would make this a negative. So I'll go ahead and take care of that. So instead of acceleration, we'll say minus g sine of theta. And finally, x as a function of time is equal to v naught t minus 1/2 g, there's a t squared here, g t squared times sine of the angle. The other way to do this is integrating. So if we know that r double dot is equal to minus g sine theta, what we can do is integrate both sides with respect to time, and you'll get the first derivative of position is equal to minus gt sine of theta plus an arbitrary constant. And what do we know? We know that our velocity at time 0 is equal to v naught. So v naught equals minus g times 0 times sine of theta plus c, or c just equals v naught. So our velocity is equal to minus gt sine of theta plus v naught. And then we just integrate one last time with respect to time. And finally, you get position, r of x, is equal to minus 1/2 gt squared sine of theta plus v naught t plus c. Now our position at time 0 is just 0. So if I plugged a 0 in here and a 0 in here, c is just equal to 0. So we can just say r of x is minus 1/2 g sine of theta times time squared plus v naught t, which is the exact same thing we got here. So cool. 2 ways to get the same answer. So now we know the position. This describes the position of the puck. Remember, it's not moving in the y direction, so we only have to worry about the x direction of motion. Now it wants to know the time that the ball comes back to the starting position, which this is our origin. So we can think of x as just being 0 there. So we can say 0 equals minus 1/2 g sine of theta times time squared plus v naught t. So this is a quadratic equation. So, our graph, this would be your x and this would be your t. I know we normally think of x being horizontal, but in this case, x is our dependent variable and time is our independent variable. So it's very possible somewhere we have two intersects along our t-axis. So the way we can solve this one, we can just factor out a t. You're left with minus 1/2 g sine theta t plus v naught. So now we have, we can use a zero product property. Either 0 equals t or 0 equals minus 1/2 g sine theta t plus v naught. Well, this was kind of redundant. That's just telling us that we're at the origin when we start a clock. We knew that. This one's pretty simple to solve. You just solve for time. I'm going to kick that bit over. So t equals 2 times v naught divided by g times sine of theta. So there you go. At that particular time, you have the ball going up the hill or up the ramp, but eventually it's going to work its way back down. And we want to know at what time is our displacement 0. And that's when it returns to its starting position. So that's all you had to do there was set your position equal to 0 and then solve for time and recognize that this is just telling us that we're at our origin at time equals 0. So yeah, that's all there is to it.